Chapter 8 talks about exponential functions and logarithmic functions in their real-world applications. This chapter is great for students to see where math is used in the real world. We're going to talk about first exponential growth and decay, and all growth means it's going up, decay just means it's going down. And these functions are used every day in banking, car loans, home loans. You talk about the census with population growth, the spread of disease. These things are very extremely common in the real world, and we will do examples of these things in class. This video is just used to get you familiar with what exponential functions are and their graphs, and pose a few questions for you to discuss in class. So here we are with exponential function notation. It looks a little bit different. The y equals a times b to the x. We're used to the x being a base, or the x, being a number that is not a power. In this case, the x is the power. So if you look, in this case, the x is the exponent. That's the difference between exponential functions. The a and the b are just constants, just coefficients. So if you look, b is the base of the power, and it's a positive number other than 1 for our purposes. It can be other numbers, but right now we're just looking at a positive number that isn't 1. X is the exponent, and a is just some real number that is multiplied by this power. So we have a is a coefficient, b is the base, and x, in this case of exponential functions, is the exponent. So when we scroll down, we're going to look at these graphs. What I want you to do is I want you to graph all of these functions. So I want you to graph y equals 2 to the x in your calculator, and then graph each one of these separate functions on a separate line so you can see them all at the same time. And if you can, try to graph them one at a time, and so you can remember which one is which. And then pause here, and then after you get those done, we'll restart the video and we'll look at what those graphs look like. Okay, so hopefully you have graphed and looked at these graphs. I'm going to show you what 2 of them look like, because I want to discuss the others in class. So here we have the original in red, y equals 2 to the x, and we have a different one of the 4 that you should have also graphed in blue, y equals 3 times 2 to the x. And what I want you to do is I want you to notice the shift, how they move, what the y-intercepts are. So keep all of these things in mind, so when we come into class we can talk about it and we can discuss the difference in these functions. Alright, so just so we can look at the graphs, exponential growth versus decay. So as I said before, growth goes up and gets really big really fast. Decay starts really big and then goes down extremely fast. I'm sorry, and then goes down extremely slow. So as you can see, it starts off really close to the y-axis and then goes, and then once it crosses the y-axis, it gets really close to the x-axis. Once it crosses the y-axis, it starts to go up really fast. And the opposite with decay. It comes down, and it goes down to the x-axis. It looks like it touches it. So what I want you to think about is, does it actually touch the x-axis? And if it doesn't, why not? Or if it does, what is the x-intercepts? And here is your notation. So we have the growth. They both look the same. They both are y equals a times b to the x. The only difference is your b in your growth is greater than 1, and your b in your decay is between 0 and 1. So numbers like 1/2, 1/3, proper fractions. That's the difference between growth and decay. The functions look the same when you're talking about standard form, but the b is what makes it growth and decay. It's extremely important. And when we look at these exponential growth and decay models, this is just a little bit of a manipulated formula. You still have y equals a, like you do up here, a, times some number, this 1 plus r, or this 1 minus r, is technically just some number, and that would be your b. And in this case, in these models, your exponent is denoted with a t, and that just means time. So usually when we talk about growth and decay models, we talk about change over time. So here we have a times the quantity 1 plus r raised to the t power. And this 1 plus r and this 1 minus r have special names. In the growth, this is called the growth factor. The growth factor. And R is the rate at which you're growing, like 5%, 10%, something along those lines. So 1 plus R would be the growth factor. Let me highlight that so you can see it. And then the 1 minus R in decay is just, instead of saying decay factor, or we say decay rate of decay. So in this case, the 1 minus R is the rate of decay. So the only difference, again, between growth and decay in these two models is one is 1 plus R, the other is 1 minus R. So in one, you're adding a percent and then multiplying it, or squaring it, or cubing it, or whatever. And then this one, you're subtracting. So that's the difference between growth and decay models. And these models are used, for instance, like population growth, or a zombie apocalypse. If one zombie bites you and then you bite 2 people and then they bite 2 people and so on and so forth. The spread of disease. And decay is usually used in science. We talk about radioactive decay, half-life, things along those lines. Or you can even talk about depreciation. That's a decay model also when you buy a car. And the last thing I just want you to see is compound interest. This is one of those real life things we're going to be working with. This is one of those things we see every day. You can ask your parents when we're paying car loans, paying home loans. We deal with compound interest. And here's the formula for compound interest. I just want you to have this in the back of your head when you come in so we can solve some problems. We've seen this before in our warm-ups, in our ACT warm-ups. A is the amount after so many years. P is the principal. That's how much you start with. That could be how much your loan is. That could be, if you're putting money in the bank, how much you initially put in the bank. And then 1 is just part of your formula. Your R is your rate, your interest rate, which is usually expressed as a decimal. N is the number of times per year that you take interest. And T is the number of years. And this is just your formula for compound interest. We will work multiple problems with this in class. So if you don't get it, if you don't understand it, it's okay. I just want you to be familiar with this formula. I want you to have seen this formula before we go into it in class. And the last thing is I want you to think, or if you have to, do some research. And it shouldn't take you very long. Just Google. And I spelled research wrong. We all make mistakes. I want you to do some research and look at some real life examples of exponential growth and or decay, and be ready to share those with your group and your classmates in class.